Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting model called as Megalodon, which is about efficient large language model pre-training and inference with unlimited context length, right? So the question is, how do you basically achieve, a transformer model, a large language model, which has very huge context length, right? So you don't need to worry about what is the size of your document and so on, just feed whatever size, right? Now, Megalodon is actually based on another architecture called as Mega, and this is pretty mathematical, as you see in the slide, but I'll try to sort of intuitively explain what the Mega architecture does, right? And once we've understood how Mega works, we can actually understand how Megalodon works, right? So in the Mega architecture, the idea is that, if you look at this one, this is basically a standard transformer architecture. It has like self-attention and feed forward. But then the change in Mega model is basically right there in this self-attention layer. So rather than using multi-head self-attention, they basically use a single head attention using what is called as the mega layer and gated attention. Okay, so that's the goal, to understand how does this mega layer and EMA and mega layer work, right? So the mega layer actually has EMA, exponential moving average, and gated attention. Okay. And why did they propose this? So why did they replace self-attention with this kind of a layer, right? So they basically did this because the main intuition, right, behind doing mega is basically explained here. They basically say that in the self-attention layer, the transformer typically does not really care about it sort of computes the attention weights independently per position in some way. So it does not really care about uh, using inductive biases across the time step dimension at all. Okay. So therefore, as a pre-processing step, so to say, what this EMA does is to essentially have the is to modify the input so that they depend on the previous time steps. Okay, so essentially the idea is that you take the input is basically x, so x is n cross d, where n is the sequence length and d is the dimensions. Okay, so you take the input x, t is the time step, and j is the dimension, particular dimension. So xtj is basically a number, as so to say. Okay, and you first expand that using a beta matrix to ut. Okay, so essentially what you have done is to basically take a number xtj, expand it to um, you know expand it to a vector ut, right? And then what you do is to essentially combine ut along with exponentially weighted exponentially weighted versions of the previous time steps. Okay, so essentially you take ut and you take alpha j part of ut and 1 minus alpha j part of the previous time steps, and you get ht. So this is like an exponentially smooth moving average value for a particular time step. And this is all being done at the input, right? So you have not yet computed QKVs and so on. So it's all being done at the input. And then, of course, you multiply it with some eta, some more weights eta d cross h, so as to basically get the revised input. So y is practically a revised input, which is an exponentially moving average smoothed version of the original input. Okay. Now, you also notice that there is another factor called as delta here, and that basically is like a damped version. So basically what it says is that while you're using this previous time steps information, you basically damp it out. Okay, so there is also a damping matrix delta, which is sort of learned. Now, of course, these alphas and deltas should basically be numbers between 0 and 1, real numbers between 0 and 1. Okay. And they're trainable, of course, right? So the main idea behind this multi-dimension damped EMA, or multi-dimensional damped exponential moving average, is to basically get a revised version of X such that it involves inductive bias from the previous time steps. And the revised version is called Y. Okay. So you basically take X and you call revised version as X dash or Y. So you can call it X dash. I mean, they basically use the same notation Y as well as X dash for the same thing. Two different notations, but you can think about this entire thing is essentially doing EMA, right? EMA. Okay, so that's basically that. So basically they do EMA so as to get a revised version of their input X. Now they use this revised version essentially. So and on top of this revised version, they basically put up further nonlinearity so as to get Z. Okay. Now this Z is basically used to extract queries and keys. So you see in this architecture in this mega layer. So this mega layer is basically being explained here, okay, in detail. So you have the original input X. You basically get the revised output X dash, using this EMA block. And then you essentially further process it to get Z. I mean, it's basically just another dense layer with a nonlinearity, right? And then you essentially do this. The typical attention computation. The way attention computation is being done is to basically multiply it with a keys vector and a queries vector, so as to get QK. And then the values are actually obtained using the original X. You don't really use the output from the EMA so as to compute the values, but the values are kept as it is from the original X. Okay. So the attention is being computed using this multi-dimensional damped EMA. However, the values still act in the original input space. Okay. So that's that. And then you do the typical softmax attention. Well, the paper basically brings up another attention function, but for all purposes of understanding, you can do typical attention computation with some relative position biases as well. And then you get the overall attention output. The overall attention output is right there. Okay. So we already talked about one change that the mega layer does so as to get inductive biases in the input, and that change is called EMA, right? Now, the other change that it does is this gated attention. Okay, so how does this gated attention work? Well, the gated attention should remind you of the GRUs. So if you basically remember GRUs, which are similar to LSTMs, however, they only have two gates compared to LSTMs, the reset gate and the update gate. Okay, so what this guy does, the mega framework does, is basically it takes this EMA processed attention output. And remember, there is only one head. So they basically show some proof in the paper that rather than having multi-head self-attention, if you do, single head exponentially moving average based attention, that's equivalent. Okay. So what they do is to combine this attention with the original input X and the EMA processed input X dash using this gating logic. So they basically first compute the reset gate gamma. As you see, it's computed on X dash, and they compute the update gate phi using X dash as well, but with a different attention, different activation, right? And then they finally basically compute the hidden layer output H dash here as a combination as a combination of, or rather using original X dash versus update, versus the reset gate, versus the attention attended input, so to say, right? So remember, O is the representation of the attention layer, right? And X dash is the representation of the EMA output in that senses. And the combination between the two is sort of being decided by this gamma factor, right? And what is gamma? Gamma is basically the reset gate. So how much do you want to reset the information, right? So that's that. And then once you have figured that out, so that's basically H dash. And then based on the update gate, you decide whether you want to essentially update a lot based on the current input or care about the previous inputs also. Okay, so that's that. Now, so far what you have seen does not, it still has quadratic complexity. Right. So essentially, what they've done is to improve on the transformer multi-head self-attention by bringing in this combination of EMA-based single head attention and the gated attention. Right. So those two combinations. However, they've done nothing to basically improve on the complexity. And transformers have quadratic complexity again because, as you see here, these computations essentially make use of all previous time steps, and that basically brings in the quadratic complexity. So as to reduce the complexity to linear, what they do is to basically divide the entire sequence into chunks of limited size, of fixed size. And then they do attention computations only within the chunks. So they split the sequence into chunks and then do attention computation within the chunks, thereby essentially trying to reduce the complexity to linear complexity. So rather than having n square as the complexity, where n is the sequence length, they basically will divide this sequence length into C chunks, thereby essentially trying to have n into C kind of complexity rather than n square complexity, right? So where C is the number of chunks. Okay. So of course, when you do this chunking stuff, you lose contextual information from other chunks. Now the idea is to still retain some sort of contextual information because the computation of every chunk essentially depends on, I mean, the first chunk here does include the computation, the EMA computation from the previous X's. So yes, there is some sort of propagation of information across chunks, but mostly the attention computation essentially happens just within the chunk. Okay. So that's that. So EMA does help somewhat in propagating information across chunks. So it's not as bad as completely isolated chunk-wise computation, but still, some of the contextual information is lost. Okay, so that's basically Mega. Now let's talk about how does Megalodon sort of build on top of Mega, right? So they basically make 4 important changes on top of Mega framework. Yeah, so I mean, this is theoretically more complicated in that senses, right? But of course, it sort of enables unlimited context length, and therefore it's interesting to know. Okay, so what is Megalodon? It is basically a model with unlimited context length. You don't need to rather worry about what is the overall size of input. So Llama 2 can only take context length of 4K, but Megalodon can potentially take a context length of millions. Okay. Um, Now, it basically extends this multi-dimensional damped EMA to complex domain. So this was the equation of multi-dimensional EMA, where if you notice there was alpha j and there was 1 minus alpha j, of course combined with delta, right? The damping factor delta. But what they do is to sort of replace alpha j with this. So alpha j multiplied by cos theta j plus I theta j. Okay, I sine theta j. So they do this, now again, so cos theta j plus I sine theta j is sort of a matrix representation where your thetas basically essentially are defined like that. So you'll have like a theta per 1 to d. So for each of those dimensions, if input was n cross d, for each of the dimensions there is a number theta, right? And then since these theta j's are themselves matrices, the way you would get the matrix is basically by saying by depending on these angles w. So where the angles w are sampled, are rather sort of not sampled, but learned, right? They essentially are of the dimensions d, and they are sort of learned. They are learned while doing backpropagation, right? And depending on these d, so overall thetas basically just include d parameters to be learned. The remaining parameters are sort of, or other, of course, theta overall is a matrix of h cross d, and it has learnable parameters only these d, right? The remaining, the h cross dimension is sort of computed using this formula. So 2 pi k divided by h multiplied by wj. So where k essentially runs from 1 to h, k runs from 1 to h, right? So essentially, once you have a wj fixed, you basically have the entire theta j vector fixed in that sense. Okay. Now you plug that in here, and essentially your alphas remain the same. Your alphas are still r d cross h, like in your mega model. However, these etas that were used in the mega model. Remember these etas which were used in the mega model to finally map your h's to the final revised input. Y. These etas are basically considered again as complex numbers. Okay. And for the sake of computing y, you only take the real part of those of that multiplication. Okay. So that's the first change. The first change that Megalodon model does is to actually expand the multidimensional damped EMA to the complex domain. The second change it does is basically to do time step normalization. Okay. Now, typical transform models do something called as layer normalization. So if there are, n different time steps in the entire sequence, what layer normalization does is to basically look at the d dimensions in every time step and does normalization just based on that. So of course it does the z-score normalization. So x minus mu divided by sigma, right? Where mu is actually computed as the mean over all of these, and sigma is also computed as the standard deviation over all of these, right? All of the all of the numbers, all of the D numbers at this time step. Okay. Now, yet another way of doing normalization is called group normalization, where you would take a few features where you basically divide these D dimensions into various groups. Okay, so let's call each group as DG, so DG numbers, right? And you actually compute normalization over DG into T different numbers, where T is the number of, or N is the number of time steps. So DG into N different numbers. Okay. Now, this is great. The group normalization is a great idea. When you essentially, when you're not in an autoregressive world, right? So group normalization can be done, for example, for BERT kind of models, right? But if in an autoregressive world, you don't have the next time step which is generated, right? So therefore, you cannot really do group normalization. So as to extend group normalization to the autoregressive world, Megalodon folks basically propose this time step normalization. What this means is that if I'm at this time step right now, I would do group normalization until that time step. So I'll basically take a particular group across each of those D things. So that's that. So here if D equal to 4, then I have defined group size as 2, and therefore I've taken the first 2. And then up to that time step, whatever are the numbers, you compute the mu and sigma based on that. Mu and the sigma based on these numbers, and then do the normalization, the typical z-score normalization. Okay, so that's how the time step normalization works. You basically take all the time steps up to time step t, and of course sum over all the groups, sum over all the elements in that group, and compute the mu and the sigma and do the normalization. So two interesting changes on top of Mega. One is the extending EMA to the complex domain, and the second is time step normalization. The third change that they do is normalized attention, and the fourth change that they do is prenorm. So normalized attention, let's talk about this. So unlike Mega model, the complex EMA model essentially, or the Megalodon model basically, of course, has the CEMA output rather than EMA. Now you notice here there's CEMA, right? However, in this, so there are a few changes here, right? So normalized attention unit essentially, compute the same x dash, it computes z, but then it also computes z dash, which is the normalized version. Okay. And then, it computes the Q and K as usual. It uses the V also as usual, which is computed directly from X rather than from Z dash. And then the O, the multidimensional, the attention value O is computed directly from QK transpose. As you see, there's no normalization required here because you already normalize the Z dash, the Z itself to get the Z dash. Okay. So that's that. And the other thing that you notice is that there is no, update gate here. So the update gate is missing. There's only the reset gate that is used. And therefore, it's still gated attention, but of a different kind. So yet another interesting thing that you notice is that there is no activation that is being used. So there is no activation for computing the Z. So in the in the Mega model, there was an activation here. They basically just removed the attention, removed the activation, removed the scaling term. Remember there was a scaling term here, which is typically set to square root of d. So remove the scaling term, and they just did normalization right there. Okay, and they use the typical softmax activation function for the attention computation. Okay, so that's that. Now the fourth change compared to Mega model is basically the two-hop residual computation. So the typical transformer models basically have this prenorm where you essentially don't do normalization later, but before. So you do a layer normalization before attention, self-attention, and layer normalization before FFN, the full the feed-forward network, right? But in Megalodon model, what they've done is to do two-hop residual computation, where you do a time step normalization before attention and layer normalization before feed forward. But you also have this interesting residual connectivity where the idea is you take the X, you do time step normalization, attention normalization, you basically get Y hat right here, okay, as a combination of the attention, the combination of this arrow and this arrow, right? So essentially attention over normalization of X plus X. Okay. Now you take the same X, by the way, and you propagate up, unlike in the typical transformer where you basically never reuse the X, right? So this doesn't go there, no, okay? But here, you basically reuse the same X. You don't really have Y hat here. You actually use X, combine it with the feed forward normalized value of y hat, and that's your final y. Okay. Now, those are the 4 changes. While training, they make yet another change. They basically use 4D parallelism. So, of course, typically people do 3D parallelism while training, data, tensor, and pipeline parallelism. But since they also have chunk-wise attention, that brings in another degree of parallelism called as time-step or sequence parallelism. Okay. So enough about the architecture. Let's talk about how does it perform. So they train the Megalodon model on top of Llama 2 architecture. So they basically use the same 7 billion parameter architecture with 32 blocks, transformer decoder, 2 trillion tokens for pre-training, and with a dimension size of 4096. While training, what they observe is that the model is able, on the x-axis compute power. So how many training tokens? So as you see, it's 2 trillion tokens. And they compare it with Llama 2 model, 7 billion, as well as with the 13 billion model. So they observe that their negative log likelihood or the training loss sort of is between Llama 2 7 billion and 13 billion. So effectively, they actually are able to obtain better negative log likelihood than Llama 2 7 billion model with the same number of parameters as well as the same compute power or training tokens, right? Since they do chunk-wise attention, they use the chunk size of 4096, which is the same as the context length of Llama 2 7 billion model. On short context, so they do evaluation, of course, on short context datasets and on long context datasets. The goal is to observe that on short context datasets, the model should not regress, right? So what they observe is that if they compare they of course therefore compare on several datasets, okay? They compare with other models. So other models, state space models like Mamba and RWKV, and also they compare with other transformer-based 7 billion parameter, 8 billion, and 13 billion parameter models. Okay. So what they observe is that on short context evaluation benchmarks, Llama 2, this is Llama 2 7 billion, this is Megalodon 7 billion, right? And what they observe is that, well, Megalodon performs better than Llama 2 for sure, yeah, of the same size. Now, clearly, it may not perform better compared to 13 billion. 13 billion is better. But you remember, they are just making you're changing the architecture of the 7 billion parameter model. So what they observe is that in most cases, you observe that Megalodon is better than Llama 2 7 billion parameter model on short context evaluation benchmarks, right? So this basically shows the power of the EMA block, right? So they clearly did not do the EMA block or the complex EMA block for improving on long contexts, right? So they basically just did so as to basically have good inductive bias carried over to the later time steps. And they observed that, yes, this helps. So the CEMA model actually helps. CMA framework actually helps. Okay, CMA framework, gated attention, all of those actually help. Now, to basically show the power of their chunk-wise attention, and how well they're able to carry forward the context across very long sequences using chunk-wise attention, they actually experiment with the long-range arena benchmark and other long context evaluation. Okay, so as part of long context evaluation, they actually evaluate over 2 million long sequences as well. And they do observe that the perplexity keeps dropping as they actually evaluate on longer and longer sequences. Okay, this basically shows that, yes, their model does not really regress with longer sequences in terms of learning. Okay. They also experiment with the Scrolls dataset, Scrolls benchmark, which basically in turn contains 3 different datasets: narrative QA, Casper, and QM-SUM. And all of these datasets, they basically observe that Megalodon outperforms the Llama 2 model. So Megalodon outperforms the Llama 2 model. Well, I mean, it is equivalent in comparison to Llama 2 long model, where Llama 2 long has been sort of trained progressively on longer and longer contexts. So Llama 2 long is actually not same as Llama 2. In fact, has been trained progressively on top of the Llama 2 model with more compute power. Okay. Now, on long-range arena benchmarks, they basically show that their Megalodon models are clearly way better compared to the Mega model, which was proposed earlier with just simple chunk-wise attention. So there are 4 things on top of the Mega model, which basically includes timestamp-based attention, pre-norm, normalized attention, and also this complex EMA. They basically lead to improvements, right? They do lead to improvements across the 6 benchmark data sets in LRA benchmark. Okay. Okay, so in summary, in this video, I talked about Megalodon, which is basically a transformer-based, improvement over Llama, or improvement over the Mega architecture, so as to support really long context lengths. Okay. Of course, the Mega architecture itself brought in a few interesting improvements. It brought in this exponential moving average kind of framework um, for carrying over inductive biases across the input, across the time steps in the input. It basically also brought in this damped EMA. So in the sense, it's good to have a damping factor for your previous time steps. Then further, it brought in this concept of gated attention. So they basically said that attention is good, but you should not always use attention. So gating is useful. They also brought in this concept of single head gated attention. So they now don't have multi-head framework there. Okay. And then lastly, they basically brought in this concept of chunkwise attention, right? And then Megalodon improved on top of these concepts further by extending EMA to CEMA. They brought in this complex stuff, a complex notation for their exponential moving average computations, right? And they also brought in this time step normalization layer rather than group normalization or layer normalization, right? Then they basically did normalized attention, then pre-norm with two-hop residual configuration, and that basically gives the overall Megalodon framework. A pretty complex framework from that perspective, but the great part is that yes, it can model sequences of unlimited length, really, right? And they basically showed the improvements over both short context as well as long context LRA kind of benchmarks, right? Of course, over short context and as well as over long range benchmarks, they basically showed that Megalodon is better than Llama 2 of the same size. Okay, so that was a quick understanding of how Megalodon works. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my search on my homepage. Thank you.